picture like a microscopic life or death claw game, but played entirely inside the human gut.
Right, yeah, which is a wild visual.
It is. And, today for you, our listener, we are opening up a really specific, highly technical piece of source material. It's a YouTube video transcript titled HCC 1475-28A Through the Scope Clips, which was uploaded by Dr. Gautamikala S. Raju.
Yeah, and it's basically a masterclass in procedural reality because I think we often treat endoscopic tools as just, simple extensions of the surgeon's hand.
Right, like a pair of scissors or whatever.
Exactly. But this transcript reveals how much complex physics and, frankly, incredibly tense human choreography actually go into deploying just a single through-the-scope clip, or a TTS clip, as they call it.
Okay, let's unpack this, because our mission today in this deep dive is to explore exactly how this tiny, seemingly simple device is redefining GI endoscopy.
It really is.
And whether you're like in the OR every single day or you're just someone who's fascinated by hidden mechanics, the margins of error we're talking about here are, they're razor thin.
Oh, absolutely. You're working in a surgical landscape that is constantly moving. It's highly vascular. The stakes are just incredibly high.
Right, so we know the primary functions of these clips, right? It's hemostasis and defect closure.
Basically stopping bleeding and sewing up holes.
Yeah, you find a brisk bleeder, you clip it, you have a perforation after removing a large polyp, you pull the edges together. But the source outlines these secondary uses that I genuinely want to puzzle through with you.
Sure.
Because if this is primarily a microscopic staple for bleeding, how does it suddenly become a GPS tracker for other doctors? Like, why is an interventional radiologist relying on a GI clip during an emergency coil embolization?
Well, so that raises a really important point about cross-disciplinary communication during a crisis.
Okay.
Because imagine an endoscopist is staring down a really brisk refractory bleed.
Like it just won't stop.
Right, it won't stop despite their best endoscopic efforts. They know at that point the patient is heading for an emergency angiogram. But the problem for the interventional radiologist who takes over is that the GI tract is vast. It's huge.
Yeah, lots of real estate.
Exactly. So finding one specific bleeding vessel on a fluoroscopy screen is literally like finding a needle in a haystack, and the clock is ticking.
Oh, I see. So the endoscopist is leaving a breadcrumb.
Precisely. They deploy a TTS clip right next to the bleeding site before they withdraw the scope.
Just as a marker.
Yeah, because these clips are metallic, right? So they're highly radiopaque.
Meaning they show up on x-rays.
Exactly. They show up as this brilliant white flare on the radiologist's screen.
Wow.
So the radiologist uses that metallic beacon to instantly direct their catheter to the exact right vascular neighborhood. It saves critical minutes that they might have otherwise spent, injecting contrast dye into all the wrong arterial branches.
That's a brilliant hack of the hardware. It's just a pinch clip, but now it's a flare gun.
Yeah, and it's not just for emergency embolizations either. The transcript details how these clips are used for laparoscopic port placement too.
Wait, how does that work?
So the surgeon takes an x-ray, they see the clips left at the tumor site by the endoscopist earlier, and they can map their surgical incisions perfectly based on that.
Oh, that makes so much sense.
Yeah, and radiotherapists use them as well to target their radiation beams so they can spare the healthy tissue around the tumor.
It's wild, but then the source also mentions these really niche mechanical uses, like using a clip to pin a feeding tube directly to the wall of the jejunum so it doesn't migrate retrograde back into the stomach.
Right.
Or researchers using them to literally anchor manometric catheters directly to the mucosa in the proximal colon.
If we connect this to the bigger picture, I think it really demonstrates how a purely mechanical tool one that was designed just to provide a simple pinching force evolves when it's put into the hands of creative practitioners.
Yeah, they really push the limits.
They do. The engineers built a localized hemostatic device, right? But the clinicians turned it into an internal GPS, an anatomical anchor, and a fiducial marker. It's just this perfect example of hardware adaptability.
So we have this single tool acting as a tourniquet, a beacon, and an anchor, but the tool obviously can't navigate itself.
No, it definitely needs a human driver.
Right, and the fact that this clip is doing such delicate work inside a dynamic, moving gut means the margin for human error must be terrifying.
Oh, it is.
And it's a two-person job, isn't it? You have the endoscopist driving the camera inside, and then the assistant is physically operating the clip handle from the outside of the patient.
Yeah, the human element is definitely the ultimate variable here. The mechanics of the deployment handle itself are Pretty straightforward.
Just a basic handle.
Basically, you have a thumb ring for the assistant's thumb and a slider that they manipulate with their forefinger and middle finger.
Okay.
It functions a lot like a syringe, but instead of injecting fluid, you are translating linear physical motion down this long, flexible catheter to operate a tiny metallic jaw inside the patient.
Right, so you push the slider forward, the clip opens, you pull the slider back, the clip closes. But Dr. Raju emphasizes this absolute golden rule in the transcript. It's a strict 3-step protocol: open, close, and wait.
Yes. The wait?
And that third step, the wait, is treated as literal life or death. The source says the assistant must never pull back further to actually deploy the clip until the endoscopist explicitly gives the verbal command.
That wait protocol is completely non-negotiable.
Really?
Oh, yeah. And what's fascinating here is thinking about the psychology of the assistant in that exact moment.
Because they can't see anything, right?
Exactly. They are standing there entirely blind to the endoscopic field. They can't see the spurting vessel. All they feel is the tactile tension of the handle in their hand, and all they hear is the endoscopist's voice.
Here's where it gets really interesting, because that dynamic, it is exactly like a sniper and a spotter.
Oh, that's a great comparison.
Right. The endoscopist is the spotter looking through the scope, aiming at the target, and the assistant is the sniper holding the trigger. But if the assistant jumps the gun-like, if they feel the tension of the closure and just automatically pull through to deploy the clip without waiting for confirmation, the source specifically says they end up occupying the real estate.
And in endoscopic surgery, real estate is your most precious commodity.
Because there isn't much of it.
Right. Look, if the clip is merely closed but not deployed, it hasn't detached from the delivery catheter yet.
So you can still take it back.
Precisely. The endoscopist can look at the monitor, realize, they haven't adequately captured the bleeding vessel, and they can simply say reopen.
And the assistant just pushes the slider forward.
Yeah, the jaws open back up and they try again. No harm done.
But once it's deployed, it's permanent.
It is permanently anchored to the tissue.
And if it's in the wrong spot, not only have you failed to achieve hemostasis, but you have now introduced a physical obstacle into the field.
You've literally placed a rigid metallic structure directly adjacent to, or even partially overlying, your target.
I was thinking about it like trying to sew a button on a shirt, but you've accidentally superglued a giant coin right over the hole.
That is exactly what it's like.
You haven't just failed to fix the problem, you've actually blocked your own access to it for the next attempt. The camera view is obscured, the next clip might deflect off the first one. You've engineered your own failure.
That analogy hits the nail on the head. You are forcing the endoscopist to perform a much more complex maneuver just to navigate around your mistake.
Right.
So it requires immense discipline from the assistant to hold that closure, feeling the mechanical tension wanting to snap shut and just wait.
So we have this really intense disciplined communication required just to avoid occupying the real estate.
Yeah.
But, and this is wild to me, even if the sniper and spotter are in perfect sync, the physical design of the tool itself introduces a completely different failure state. Dr. Raju calls it a superficial closure.
Right. This is where human intent kind of collides with mechanical reality. Well, a superficial closure occurs when the clip is successfully deployed, but it only grasps the very uppermost layer of the mucosa.
Like it just pinches the skin on top.
Exactly. It doesn't get deep enough.
The source notes that in these cases, you can actually see a visible gap between the two blades, and only about a quarter of the blade length is actively engaging the tissue.
Right. The other 3/4 are just empty space.
My immediate thought reading this was, wait, if the doctor is aiming perfectly and the assistant closes exactly on command, why wouldn't the jaws sink all the way in? Like, why is the tool failing to grab the deep tissue if everything was done right?
That comes down to the inherent mechanical retraction of the device itself.
Retraction.
Yeah. As the jaws of the TTS clip transition from being open in a V shape to being closed in parallel, the pivot point at the base of the jaws is physically drawn backward into the catheter sheath.
Oh, I see.
So the entire clip physically pulls away from the target tissue by several millimeters during the actual closure stroke.
Wow. So the literal act of grabbing pulls the tool away from what it's trying to grab.
Precisely. If the assistant simply pulls the slider back at a normal, fast speed, that rapid backward translation of the pivot point yanks the jaws away just as they're coming together.
So they slip?
Yeah, they scrape across the surface and they only pinch that superficial mucosa.
And that's bad because the gut is always moving, right?
Very bad. In a highly active gut, a superficial clip is just going to slough off in a few hours.
Oh, man.
Yeah, so if it was holding a brisk bleeder, the patient rebleeds. If it was closing a perforation, you suddenly have a recurrent defect and a massive infection risk.
All because of a millimeter of mechanical retraction.
Yeah.
A tiny retraction causing a catastrophic clinical failure. So how do they actually solve for this? Because they can't change the physics of the clip, right? How do they achieve what Dr. Raju calls a deep closure with no gap?
Well, they can't change the physics, no, but they can neutralize those physics through countertraction.
Countertraction, okay.
This is really where the microchoreography peaks. To achieve a deep closure, the assistant has to completely change their technique. They cannot just snap the handle closed.
I have to go slow.
Exactly. They must execute a deliberate, highly controlled, slow closure.
Giving the endoscopist time to react to the movement.
Right. As the assistant slowly pulls the slider back, the endoscopist feels the commencement of that backward retraction. And simultaneously, the endoscopist applies gentle forward pressure on the entire endoscope, or the catheter itself.
Wait, so they physically push into the retraction?
Yes.
So if the clip inherently wants to pull back 3 millimeters, the endoscopist manually pushes forward 3 millimeters at the exact same time.
They are completely canceling out the backward vector.
That is so cool.
It is. By maintaining that forward pressure during the slow closure phase, the tips of the blades remain buried deep in the submucosal layer.
Ah, so they don't slip out.
Exactly. So as the jaws meet, they encompass the full thickness of the target tissue. The result is a perfect, deep closure, utilizing the entire length of the blade with absolutely zero gap.
It's literally a microscopic real-time physics equation performed by 2 people who can only communicate through voice and the tactile feedback of a plastic handle.
It's a dance.
It is astounding. But, let's push the limits even further, because neutralizing mechanical retraction works beautifully for, like, a standard vessel or a small defect.
Sure.
But what happens when the endoscopist is staring down a perforation that is physically wider than the maximum open span of the clip's jaws? You can't just push forward to solve a hole that's simply too big.
No, you can't. And this brings us to the advanced defect closure techniques pioneered by Dr. Yahagi.
From Japan, right?
Yes. When the standard application parameters fail, you basically have to manipulate the biological landscape to fit the tool.
Right. And Dr. Rogers' transcript outlines several of Dr. Yahagi's methods, and I really want to puzzle through the mechanics of these with you.
Let's do it.
So the first one is straightforward, but seems like it requires a lot of guts. You deploy one arm of the clip into the mucosa on one edge of the hole, and then you physically drag that tissue across the open void to the opposite edge before closing the second arm.
Yeah, it is essentially using the clip as a tiny grappling hook.
But isn't the risk there tissue tearing? Like, the GI mucosa is pretty delicate, right?
Extremely delicate. If you apply too much lateral traction, the clip's teeth will simply rip right through the tissue.
And then you've just made the hole bigger.
Exactly. You're expanding the very defect you're trying to close.
Which perfectly explains his next technique in the source. Because it says if the tissue is tight or slippery, Dr. Yahagi uses an electrosurgical knife to make a tiny mucosal incision, like a deliberate cut, near the edge of the defect.
Yeah.
And at first, reading that, I thought, why on earth would you make another hole next to the big hole?
It seems counterintuitive.
Right. But it's to create a localized flap, isn't it?
That's exactly it.
It gives the teeth of the clip a deep perpendicular edge to actually bite into. So when you apply that dragging force across the gap, the clip has a structural anchor, and it won't just slip off the smooth surface.
You are engineering your own anchor point.
But it's genius.
It is. But what if the tension across that gap is simply too massive for a single clip to hold, even with a great anchor?
Okay, this is where I really struggled to visualize it from the text. The figure 8 double ring method. How does that physically work inside a 3D tubular space like the colon?
Okay, so think of it as a microscopic pulley system.
A pulley system.
Yeah, you deploy your first clip on one side of the massive defect. Now, every single clip has a small metallic ring or a hinge right at its base.
Okay, I'm picturing that.
So you take a second clip and you pass its open jaws literally through the base ring of the first clip.
Oh.
And then you drag that second clip across the gap to the far edge of the defect and deploy it there.
Wow. So you aren't actually pulling tissue to tissue anymore. You are pulling clip to clip.
Right. By linking the two clips together in a chain, you distribute the mechanical tension across a much wider surface area.
So the metal takes the stress, not the skin.
The metal takes the brunt of the load, not the fragile mucosa. It's a brilliant application of structural engineering inside the human gut.
That is wild. The transcript also mentions using auxiliary tools like loops, specialized graspers, or endoscopic sutures to physically haul the really wide edges together into like a tented shape before throwing clips across the base to lock it all in.
Right, building scaffolding.
Scaffolding, exactly.
Right.
But I mean, all of these pale in comparison to how he handles massive transmural perforations, like the really big ones.
A momentum technique.
So what does this all mean when we talk about the omentum? Because this is where Dr. Yahagi's ingenuity completely rewrites the rules for me.
That's a game changer.
For you listening, if the perforation is so massive that standard clips, anchors, and figure eights won't bridge the gap, the transcript describes the endoscopist utilizing the omentum. What even is that?
The omentum is basically the body's internal policeman. It's a layer of fatty tissue that naturally migrates toward areas of inflammation or perforation in the peritoneal cavity to wall them off and protect the body.
Wait, so if the hole in the gut wall is gaping wide open and that external omental fat is visibly sitting right outside the defect,
Yeah.
Dr. Yaki's method is to reach the clip through the perforation, grab the external omentum, physically drag it inside the lumen of the gut, and clip it to the mucosal edges.
Yes. You are completely co-opting the body's natural defense mechanism.
You are literally pulling the outside in.
Exactly.
You are using the external fatty tissue as a biological cork and just stapling it to the inside of the organ to seal the breach. The sheer spatial awareness and lateral thinking required to look at a massive hole and say, you know what, I'll just grab the insulation from the outside of the house and pull it through the drywall to plug the leak.
It's incredible. And if we connect this to the bigger picture of advanced endoscopy, it proves that clinical mastery isn't just about executing a rigid set of steps from a manual. It is about deeply understanding both your mechanical limitations and the biological properties of surrounding anatomy, and then dynamically combining them to solve an acute crisis in real time.
Yeah.
Dr. Raju's breakdown of Dr. Yahagi's techniques really highlights a shift from basic hemostasis to true, complex endoscopic surgery.
It changes entirely how you view these procedures. I mean, the next time you, our listener, encounter a discussion about minimally invasive GI interventions, you won't just picture a camera and a screen anymore.
You'll know the hidden choreography.
Exactly. You'll know about the sniper and spotter discipline required to avoid occupying the real estate.
You'll understand the millimeter-precise countertraction needed to neutralize mechanical retraction and get that deep closure.
Right. And you'll appreciate the sheer architectural genius of figure-eight pulleys and omental patches. It is a meticulously timed, high-stakes dance.
And a profound reminder of the precision required when human hands operate through the narrowest of margins.
It really, really is. And, you know, analyzing the mechanics of that clip today, it leaves me with a thought I just haven't been able to shake.
Oh, yeah. What's that?
Well, we spent a lot of time breaking down the physics of retraction, right? How this incredibly useful, life-saving tool inherently pulls back from its target by a few millimeters at the exact moment it's supposed to engage.
Right, the backward pull.
Yeah. And if the team operating it doesn't anticipate that invisible limitation, if they don't actively push forward to compensate, they achieve nothing but a superficial closure that ultimately fails.
The mechanical reality completely overriding the human intent.
Right. And I think that's a fascinating lens to leave you, our listener, to look through today.
How so?
Consider the retractions in your own complex systems, right? Whether that's your workflow, your communication, or the tools you rely on every day. Just like the TTS clip, how many of our systems inherently pull back or fall short at the exact moment of execution?
That's a great point.
And how often do our plans fail simply because we don't anticipate that invisible mechanical limitation and we fail to gently push forward to compensate for it?
Wow.
Something to think about. Think about where you need to apply that deliberate forward pressure in your own life to achieve a deep closure.